Yeah, good afternoon. Let's start. So, am I audible or my screen is visible, right? Okay. Yeah. So now let's start. So um, I think yeah. So this week today I will solve some sample problems, five to six sample problems only. Because the theory what I covered last week that is only done in the this week 10. Okay, so I'm saying that in week 10 what professor has already taught that I revised that in last week. So this week there is no that there is so there is not that much theory. I will just solve some sample problems. Okay. So the first problem is that on the basis of complete sensing, so consider the sparse signal estimation problem. Problem as shown below. Suppose this is the matrix 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, then so this is the sparse signal recovery problem. So this matrix is called the measurement matrix or observation matrix that is named as phi, and this is the sparse signal vector x, and this is the observations y. So the system model is phi x is equal to y. Now we need to find out estimate x using these equations. Okay. Uh, yeah, but X is a sparse signal, so we can follow some greedy algorithm. So the H0 norm problem, the H0 norm minimization problem is is a NP-hard problem. Its complexity is very high, so we can solve this by a greedy algorithm now. For so that will be easier to solve. Suppose we can solve it by using OMP, orthogonal matching pursuit algorithm. This is a greedy algorithm. So solving by orthogonal matching pursuit algorithm. So in the OMP algorithm, at the beginning to uh, we need to set the residue. So residue is so residue is equal to R. So at the beginning, we need to set residue as equal to or as same as the observation Y. Okay. So this is the first step. So residue R equal to Y. Then we need to find out what is the lambda. Lambda is equal to R transpose phi. So the algorithm or the process I have written in the last class. So so the OMP algorithm is written here. So first we need to set residue as same as the receive vector y. Then we'll run a loop. So this is the loop. This is a loop. So we'll run a loop and we'll find out r lambda equals to r transpose phi, and we find out the maximum, the position of the maximum absolute value of the lambda, and then we'll find out that column of the measurement matrix, and then we'll find out the sparse vector x by using this pseudo inverse of the pseudo inverse of a into y. So this is the process. So I will just follow this process, this algorithm, to estimate the sparse signal at the last. So lambda equal to r transpose phi and mod of this. So that is equal to r is y. So y is equal to 143. Okay. So r transpose is 143. So it's a row vector, and phi is 0 0 1, 0 0 0, then 1 1 1, 0 1 0, then 0 0 0, 1 1 1. That was the phi. So this so that is equal to uh, so this is the 1 cross 3 vector, and this is the 3 cross 1 2 3 4 6 6 vector. So so that will be 1 cross 6 vector. So 1 4 3. So that will be 4 the first position. Then in the second position also 4. Then in yeah. So then 4 1 4 3 8. Yeah. So then 4 4. Then 1 and 1. So 5 third position, and then 3, and then 7 fifth position, and then 3. Okay, so this is the 1% basic vector. So very pointy step I can write down. Okay. So, so first element will be 4, then second element will be 4 again, then 1 plus 4 5, then 3, then 4 plus 3 7, then 3. This is the 1 plus 6 vector. Now we need to find out the max position of the maximum value of this. So S is the position. S will take the position. Position is 1, 2, 3, 4, 5, 6. So out of 6, only this position is the maximum value. So the S will take one. S is just a set of S is just a vector. So that will take 5. Okay, because this is the fifth position. 1, 2, 3, 4, 5, 6. So at the fifth position it's maximum. This will take 5. Then I will find. Then in the third step, let's A will form a matrix A, which will take only that column of so phi of this index. Okay. So that means it will take a column vector. So 5, fifth column. So that is 0 1 1. This column 0 1. Then what is the x? X is equal to uh, pseudo inverse of A into Y. Pseudo inverse of A, that is A transpose A transpose A inverse A into Y. That is equal to A transpose A. So A is just a column vector, 3 cross 1 column vector. So it will be 0 1 1. then 0, 1, 1, this inverse, then 0, 1, 1, then into y is equal to, sorry, this will be also A transpose. 0, 1, 1, then y is equal to 1, 4, 3. So this is 1 plus 1, 2. So 1 by 2 into this is the 1. So 4 plus 2 is 7. So this will be 7 by 2. So x is just one value. So then residue will calculate. That is the fourth step. Residue is equal to y minus this uh, a into x. Okay. So that is equal to y was 1, 4, 1, 4, 3. This minus a was just a column vector 0, 1, 1 into x was 7 by 2 is equal to, so 1 minus 7 by 2 is 0, and then 4 minus 3.5, then 3 minus 3.5, that is equal to 1 point 5 minus 0.5 is the residue. Then I will again go here and follow the same process. So then, so the second step will give R. So lambda is equal to R transpose phi. Full value of this. So this is equal to 1 0.5 minus 0.5. This into what was the phi? Phi was 0 0 1 0 0 0. Then 1 1 1 0 1 0 0 1 0, then 0 0 0 1 1 1. So that is equal to 0.5 0.5 1 so this is the 1.5 1.5 and then minus 0.5 then this is 0 and then this is minus 0.5 and actual value of this, so this minus will become plus and this will also become plus. So then the position, so this is the first position, second position, third position, fourth position, fifth position, and sixth position. Of this, which entry? So which, so then S will take. Last time it was the fifth position, right? Fifth position. Now it's taking third position. So 3, 5. Now this is a vector, and then they will give A is equal to phi of. So earlier it was so earlier, yeah, phi of colon 3 comma 3, then phi colon 5. That means it will take third column, and fifth column. So that is equal to third column was this thing was 110 and then fifth is 011. So 110, 110 and 011. So this is the A matrix. Then so X will be so then X will be A dagger Y that is equal to A transpose A inverse A transpose into Y that is equal to 0 not 0 This is 1 1 0 0 1 1 into 1 1 0 0 1 1 is inverse into A transpose is 1 1 0 0 1 1 into y is first 1 4 3 1 4 3. So this becomes 1 plus 1 2 2 then 1 0. So this is the 1 then 1 plus 1 2 inverse of this into 1 plus 4 5 and then 4 plus 3 7. So it's equal to 4 minus 1 3. So 1 by 3 into 2 2 1 1 minus minus 5 7 equal to 5 10 minus 7 3 3 10 minus 5 plus 14 14 9 1 and 3. So this is the estimate of non-zero elements. Okay, 1 and 3. So and then what is the residue now? So residue is equal to y minus a x. So equal to y was the 1 4 3 and a is 1 a is 1 1 0 0 1 1. So 1 1 0 x 1 3 is equal to 1 4 3 minus. So this is 1. This is 4. This is also 3. Then residue is 0 now. Okay. So it converges. It converges now. So ultimately you will get the hence it converged already. It is converged already. So the positions of non-zero entries is equal to S. So S is equal to 3, 5. So third and fifth positions are non-zero. So 3, 5 that is equal to 3, 5 and the values is equal to this x is equal to here this 1 1 3. So the sparse estimate x. So the sparse signal recovery. So the sparse signal estimate so only out of 6 positions, only third and fifth positions are non-zero, and so everywhere else it's 0. So, 0, 0, 1 first, second, third position is 1, and then fourth 0, and fifth position its value is 5. Sorry, value is 3, then 0. Okay, so this is the non-zero, this is the non-zero. It is first. So this is third and fifth position. So this is the problem of the Sparsimal recovery. And second problem is that on the dual problem. Okay. So there is one problem minimize. So find the dual problem. The following optimization problem. The optimization problem is that minimizing x transpose x. X is a vector subject to ax equal to b. Okay. So the solution as follows. So, so first we need to find out the Lagrangian. So Lagrangian of x comma lambda. Where this x comma lambda means Lagrangian means this fx, this objective function plus lambda into this a x minus b you can write down because so that same as x minus b is equal to 0. So the same thing, so x minus b we can write down. Then we need to find out another function q of lambda that is uh, only a function of lambda, not x. So that is the increment with respect to x of L of x comma lambda. That means we need to derive, we need to differentiate lambda, sorry, not lambda, we need to differentiate L with respect to, with respect to L, and then with respect to x. And then we need to find out the minimum value of Lagrangian. And then we put that value here, and we will get q of lambda. So there is so differentiating with respect to x, we will get q into x plus 2 into x plus um, a transpose lambda is equal to 0. Then x is equal to minus of half a transpose lambda. Then we put this value here. Then we get q of lambda. So q of lambda is equal to put that value. So x is equal to half minus of half a transpose lambda. So it will be 1/4 lambda transpose a transpose lambda in class of lambda into ax. A into x equals to minus half of a transpose lambda x minus b is equal to 4 under 4 lambda transpose a transpose lambda plus minus 4 to be minus 1 by 2 lambda correct. Now it's fine. Yeah. So it will be lambda transpose a transpose lambda minus lambda transpose b. So it will be minus 1 by 4 lambda transpose a transpose lambda minus lambda transpose b. So optimization problem is that the dual problem. So dual optimization problem maximizing minus 1 by 4 lambda transpose a transpose lambda minus lambda transpose b subject to non-position equal to constant. So this is the dual opposition problem. Mm, so then the third question is so first question. So what is the dual problem of? It's a linear programming problem. So C transpose is subject to equal to B and x greater than equal to 0. So there is one linearity constant as well as there is one equality constant as well as one inequality constant extra here. So this kind of how to find out dual problem of this LPT problem I had solved that in the last class. So here so you see that this is a dual problem basics in linear yeah, so this is the finding the dual problem of the linear program very basic. So here I found that the proportion is same. So then I found out the dual problem of this linear program problem. So the dual problem means that this thing this is the dual problem. This is the dual problem. Okay. So this you can see that the last lecture I solved that thing. Okay. So um, with after that we need to see the okay so optimal power allocation for the frequency selective channel. So the optimal power allocation for the frequency selective channel is that so you consider the OETM optimal frequency division multiplexing OETM. So the scheme is like that in the case of OETM. So there are n number of subcarriers. So Here, here is a zero subperiod, first subperiod, then n minus one. So, so n minus one subperiod. Okay. So n number of subperiods are there, and this x-axis is the time domain. Okay, there is the symbol. So suppose this is the first original symbol. So first, like the second, original symbol one, two, like that. So element of original symbol. So, so this is the subperiod. So for each subperiod, the equation system model will be as follows. So, so I is equal to hi to xi plus wi. That is I is equal to 0, 1, so for n minus 1. For each subperiod, it's just like flat fading channel. Okay, so there is one attenuation constant hi, and that is multiplied with the transmitted symbol xi. Okay, so this is the system model input output relationship for each subcarrier in the case of octagonal frequency division multiplexing. Okay. So now we need to find out the capacity. So for each, so each path is parallel. Okay, one path is independent. Each path means each subcarrier. So for each subcarrier is independent of another subcarrier. So we can find out the this is a parallel channel. Okay, so one subcarrier is parallel to another subcarrier. So we can find out the capacity of each and every subcarrier. We can add this capacity and get total capacity. So C total is equal to summation of I equals to 0 to n minus 1 Ci. Now what is Ci? Ci is the capacity of ith subcarrier. So what is the Ci? Ci is the capacity of ith subcarrier. So that is the log 2 1 plus SNR. So 1 plus SNR of each subcarrier. So this is the signal. SNR is the signal power by noise power. So signal is this whole is the signal. So this is the mod Hi square, and mod Xi square is the Pi, the input power on each subcarrier, the transmitted power on each subcarrier. That is the Pi divided by noise power. Using this noise power is sigma square. So this is the capacity of ith subcarrier. Now total capacity is equal to summation of Ci I equals to 0 to I goes from 0 to n minus 1. That is equal to summation of log 2 1 plus sigma square equals to 0 to n minus 1. Then then we need to find out this capacity to be maximum for the with respect to this pi. Okay, we need to find out the optimal pi so that this capacity is maximum. So our optimization problem is that maximize this summation of I equal to 0 to 1 log 2 1 plus mod hi pi by sigma square subject to summation of pi equal to 0 to n minus. That should not exceed the total power. That is same as the total power available for all the subcarriers, and pi is greater than equal to 0 for all lines. So this is the optimization problem. So solution, how to solve? So we need to find the Lagrangian. So Lagrangian A is equal to objective function I equal to 0 to n minus 1 log 2 of 1 plus mod of hi square pi by sigma square plus lambda into summation of I equal to 0 to so summation 0 to pi n minus 1 minus p total. Okay, now we need to find out the maximum is this. Okay, and this pi is should be greater than equal to 0. Okay, now we can find out, we can derive, we can differentiate L with respect to each pi. Okay, that is equal to 0. We can find out, and then pi equal to pi star we can write now. Okay, so that is itself giving us like 1 by log 2 base e into 1 by 1 plus pi star e I mod square by sigma square into mod square by sigma square minus lambda is equal to 0. Ultimately, we are getting pi star equals to 1 by lambda prime minus sigma square by mod of hi square plus where this lambda prime is equal to log 2 base e multiplied with lambda and h plus is where this function plus is that h plus is equal to max of x comma 0. Or you can write down this is as same as x when is greater than equal to 0 and 0 when x greater than equal to 0. Okay, this is the pi star optimal power. Okay, so we can okay, so then how to choose this lambda? Okay, so, so you can find out lambda by using the constant power constant. So choose this lambda times such that summation of pi star equal to p total. So this is the optimal power for the frequency selective channel. Now for the minor channel, these are the transmit antennas. The receive antennas are as follows: one, two, inner number of receive antennas, one, two, 20 number of transmit antennas. Okay. So the system is as follows: y equal to h x plus w. Okay, so this y is a vector of nr cross 1, so h is a matrix of nr cross nt, and x is the nt cross 1, w is also nr cross 1 vector. Okay, now how to find out the optimal power. Okay, so we have so I have taught the singularity composition in the second class or third class maybe. So the basic is that H is a matrix, inner cross empty matrix. So H we can write down H as a singular value. So H as the U H is same as U sigma V Hermitian. Okay. So and sigma is the diagonal matrix which contains the singular values. Okay. So then U and V are the unit matrices. process. Okay. So now we can so one thing that we can so ultimately y equals to h is the u sigma v are machine u sigma v are machine to x plus w. Now we can send x tilde, not x. X tilde is equal to what x tilde is equal to v into x. We can send v are machine. Okay, v are machine here we can send. Okay, then ultimately x equal to I mean, x we are sending and x tilde is equal to the admission x. Okay. So x equal to d into x tilde. So that means y equal to u sigma and the admission is identity. So x tilde plus w. Then y tilde is equal to we can multiply that using y admission that is equal to and this will not change the capacity because it's a unitary transform. That's why. So sigma x tilde plus q one so that thing whole thing you can write down w tilde is equal to sigma x tilde plus w tilde y tilde is equal to this is the new system model now. So that means y tilde one is equal to sigma one x sigma one x one plus w tilde one and then y2 y tilde 2 is equal to sigma 2 x2 plus w tilde 2 which is the rank is r so y r y tilde is equal to sigma r xr plus w tilde r then y r plus 1 so r is the rank. Okay, so y r plus 1 is equal to 0 so because sigma r plus 1 sigma r plus 1 equal to sigma r plus 2 dot sigma uh, dimension of sigma dimension is the 0 all at the higher sigma value is 0 so then this is the sigma r plus 1 tilde then y tilde in r to y so then ultimately the capacity is so Ci is equal to log 2 1 plus sigma I square by sigma square into Pi. Okay, when I is equal to 1 to r, not NR or NP. Okay, so C total is equal to summation of I equal to 1 to r that is equal to summation of I equal to 1 to r log 2 1 plus sigma I square Pi by sigma square. Now the operator problem is that maximize PC total. Um, Let me maximize this summation I equal to 1 to r log 2 of 1 plus sigma I square pi divided by sigma square subject to summation of pi I equal to 1 to r equals to 2 total and pi is greater than equal to 0 for all I. Okay. So the solution is the water being just similar to water being the solution. So this is the water being solution. So the solution is called the water being solution. The water being solution. So water heat solution. So water heat solution. So So optimal power Pi star is equal to 1 by lambda minus sigma square by sigma I square. Okay, plus so by lambda is chosen in equal power constant that is Pi equal to 1 to 1 is to P total. Okay, so so we can solve a problem. Question is that so suppose P theta let P total is equal to um, 2 and sigma square is equal to 16 and sigma I equals to 2 comma 4. There are two singular ones. Okay, so what is the optimal value? So P1 star, what is the P1 star and what will be the P2 star? Okay, so this is the singular value. So this is the mode 1 and mode 2. Okay, so then so using the formula of P1 star is equal to 1 by lambda minus sigma square. Sigma square equal to 16. 16 by sigma square equals to 4. So it equals to 1 by lambda minus 4. P2 star is equals to 1 by lambda minus 16 by 16. Equals to 1 by lambda. So the 1 and 4. So 1, so this is the 4. First one is 1. So first one is 4. So okay, the difference is 3, but the optimal power is the sorry total power budget is 2. So if 1 by lambda is here, then the total required power budget will exceed 3. Okay, but here the available power budget is 2. So then that 1 by lambda can't be here. So that will be below this 4. Okay, so that means so lambda should be below 4. Here power allocation here. Okay, and here there is no power allocation for the singular mode one. Okay, only in the singular mode two the power allocation is there. So P1 one star is equal to 0 and P2 star is equal to 1 by lambda minus 1. So P1 star plus P2 star equal to P total. So 0 plus 1 by lambda minus 1 is equal to P total equals to 2. Okay, that is equal to 1 by lambda minus 1 equal to 2. So 3. So 1 by lambda equal to 3 is equal to 3. So lambda is equal to 1 upon 3. So P1 star is equal to 1 by lambda minus 1. So 3 minus 1 that is equal to 2. So total power it will get. So P1 star equal to 0. So this is a P2 star. So then this P2 star is equal to 2. Without power allocation. So to maximize the capacity. Then the next question is yeah, so, yeah, that's all for today. So these are the problem question, sample problems. Okay. If you have any doubt, you can ask me. In the first question, I have solved how to estimate the sparse signal or how to recover a sparse signal using a underdetermined system. So this is I decided I solved using the optimal matching pursuit algorithm. Then in the second question, find so I have solved how to find the dual problem of the of some convex optimization problem. So first one is the convex optimization problem. Second, a quadratic optimization problem, and second one is the LPP problem, linear programming problem. For the LPP problem, I have solved that problem. How to find out the dual optimization problem of that of the linear program problem. I solved that question in the last class. For optimal, what is the optimal power allocation for the OFDM, optimal frequency division multiplexing, and what will be the optimal power allocation for the MIMO channel? So those things I have solved here, and I have taken one example of MIMO channel capacity. What will be the optimal power allocation? So we can check that in assignment similar questions can come. Okay, and the process and the process is same. Okay. Thank you.